Please.
Thank you for the introduction, and thank you for the invitation to talk here. And I will talk about a recent research project, which is a joint work with Michal Opler and Jakub Pekarek, and it has to do with sorting. So let me begin by explaining what I mean by sorting a sequence. So I imagine that I have a sequence of n distinct numbers. I might as well imagine that those are numbers from 1 to n in some order, and I'd like to sort them, so transform them to be in increasing order. And in my model of sorting, I imagine that I have some fixed set S of operations that I'm allowed to perform on a sequence of numbers. So let's say in this picture, suppose I'm allowed to take the first number from the input and move it to the third position, and move the second number to the first position, and the third number to the second position, and this gives me a new sequence of numbers. And I assume that this set S of mine is just a set of some permutations that I'm allowed to perform regardless of what the input is. And by choosing my operations wisely, I might eventually end up with an increasing sequence of numbers. And the goal is to arrive to a sorted sequence of numbers in as few steps as possible, and the smallest number of steps that I need for a given input is the sorting time of the input with respect to the set of operations S. And it might happen that this sorting time is infinite in case I'm not able to sort the input at all. And what I really be interested in is the worst case sorting time for the set S and the length of input n, which is the maximum sorting time over all possible inputs of length n. Let me go through some examples so that at least the definitions are clear. Mm-hmm. So suppose, some examples of sorting in this model. So perhaps the simplest procedure, or the simplest set of operations that you can imagine, are the adjacent transpositions, where you can just switch the ordering of two adjacent elements. And to sort an input in this model is essentially to run some form of bubble sort. The sorting time of a given input will be the number of inversions, and the worst case sorting time will be exactly n choose 2 attained for the decreasing sequence. Another possible set of operations is what I call the move first element type of operations, where I'm allowed to pick the first element of the input and move it to some other positions and move some subsequent elements to the left to make space for it. And here you have no problem convincing yourselves that the worst case sorting time will be n-1 on inputs of length n. So those are easy examples where I'm able to determine the worst case sorting time exactly, but that's rather an exception than a rule. In fact, even for quite a simple set of operations like these prefix reversals, where I'm allowed to take some prefix of the input sequence and reverse it, even for such set of operations, the exact sorting time is not known. This is a somewhat well-known combinatorial open problem known as pancake sorting, where you imagine that you have a stack of pancakes of different sizes, and all you can do with it is to pick up some number of pancakes from the top and flip them over. And the question is how many flips you need to sort them. And it has been known, and it's easy to show that this worst case is linear, but it has been like an open problem since 1970s to give some precise value for this worst case sorting time. Even precise value for the leading multiplicative constant is not known. But in my talk, I don't care about multiplicative constants at all. So for me, if somebody tells me that a set of operations has linear worst case sorting time, that's perfectly acceptable answer. And unfortunately, in some cases, I don't even have this level of precision. Here's a type of operation known as parallel block reversal, which does this. It partitions the input into blocks of consecutive entries, any number of blocks, any size of blocks, and then in one step, I reverse each block. And for these operations, best I can tell you is that you will need, in the worst case, at least order of log n steps. But the best upper bound I can give you is order of log square n. So I don't even know the exact asymptotics. So with these examples, it should be clear what I mean by a worst case sorting time. And I told you that I'm interested in the asymptotic behavior, but for a general set S of permutations, this doesn't make much sense because, I mean, if there is no restriction or no connection between what I can do to inputs of size n and what I can do to inputs of size n plus 1, then how can I even talk about asymptotics? So I will not be looking about completely general sets S. I will be looking at sets which are hereditary, or permutation classes, as they are also known. And to describe what I mean by hereditary, I have to describe what I mean by containment of permutations. And I'm using what is perhaps the most common notion of permutation containment, where I say that a permutation of length k is contained in a permutation of length n, if this permutation of length n contains a subsequence of length k whose elements it sorts in the same way as the permutation of length k sorts its elements. So here, picture shows a permutation of length 4, which is contained inside this permutation of length 7, as witnessed by these 4 elements which are sorted in the same relative order as in this particular permutation. And once I know what containment I'm considering, I can define what a hereditary set of permutations is. That's just a set which, for every permutation, also contains all permutations that are contained in it. And in this area, hereditary sets of permutations are also known as permutation classes, and that's the terminology that I will be using. And now I can finally tell you what question I will be addressing. So the question is, what are the possible asymptotic behaviors of the worst case sorting time for a permutation class? And I will not leave you in suspense for too long. This is the answer to the question, or at least the answer as we have it at this point in time. So for any permutation class, there are 5 possibilities that may occur. Either the worst case sorting time will be plus infinity for every n large enough, meaning that the class is too small to sort all permutations. Or else, if the worst case sorting time is finite, then it will be at most quadratic in n, and there are examples of permutation classes where the worst case sorting time is quadratic, such as the adjacent transpositions that I have shown you a while ago. Now, if the worst case sorting time is subquadratic, then it will be at most linear. And there are examples of permutation classes whose worst case sorting time fits in the range between square root of n and linear. And if the worst case sorting time is even smaller than order of square root of n, then it will drop to log square. And again, there are examples of permutation classes where the worst case sorting time is between log n and log square n. And if the worst case sorting time is even smaller than logarithmic, then your class contains all permutations and it can sort any input in just one step, and the worst case sorting time is 1. So this is how our knowledge stands at this moment, and you notice that there are some gaps or cases where the lower bound does not quite match the upper bound, and those gaps are probably due to our ignorance. Specifically in this case number 3, I'm including all classes which have worst case sorting time somewhere between square root and linear. In fact, all the classes that we know of that fit into this range have worst case sorting time, which is linear. So it might very well happen that instead of omega square root of n, I should just write theta of n. That at least would be my guess. So the square root is just an artifact of our incompetence at proving lower bounds. And also in this type 4 that you see here, there's a gap between log n and log square n. And again, in this case number 4, actually all the classes that fit into this range for which we can determine the asymptotic sorting time, well, at least up to multiplicative factors, end up having logarithmic sorting time. So for all we know, it might happen that this log square can be replaced with O of log n. Here I'm not quite sure if this is what we should believe. It might also very well happen that this case number 4 is well, actually several different cases where some classes have sorting time of order log square and others of order log n. And I mean, a priori, there's not even any clear reason why to expect that the worst case sorting time is some well-behaved function. There might be some kind of strange oscillation where this function sort of fluctuates between, say, log n or log square. I cannot prove that this doesn't happen. Then again, I don't have any example where this would happen. And so I will tell you in a moment a lot more about these classes of polylog behavior. And in general, what I will talk about today is what happens with these large, say, classes where the sorting time is either polylog or at most linear. If you are interested in knowing which classes have infinite sorting time or quadratic sorting time, or how does this gap between quadratic and linear appear, do feel free to ask me afterwards, but I will not include it in this talk. So now for these cases 3, 4, and 5. So let me start at the bottom. So the class that has a sorting time equal to 1 is fairly boring. It's the class of all possible permutations. And the only slightly interesting aspect here is that if the sorting time is more than 1, then it jumps all the way to logarithm. So why is there this gap? And that's actually a very simple argument. So I will show it in full. Well, it's a simple argument if you know the theory, and an important part of the theory here is the Marcus-Tardosh theorem.
Have you seen immediate questions?
If S was the set of all involutions, then I think the worst case sorting time is 2 for the set of all involutions. So you are telling me
you may defer it to the end of the talk, but just don't let it disappear. No, okay.
Right. It is not the case that any permutation can be obtained by composing two involutions. And actually, are involutions even hereditary? No, they are not. So involutions somehow fall away from the scope of what I'm talking about here. So they do not seem to be a counter example to what I'm claiming. I hope that this addresses the concern in the chat. Right, so why is it that every permutation class that does not contain all permutations has a log n lower bound? Well, that's because the Marcus-Tardosh theorem tells us that every permutation class that does not contain all permutations contains at most k to the power of n permutations of length n for some constant k. And from this, as a fairly straightforward corollary, you obtain that for every such permutation class, the worst case sorting time is at least order of log n. Why is that? Well, it's because of counting argument. So say I have this permutation class S. It has at most k to the power of n permutations of size n. So how many inputs can I sort in at most t, or say exactly t steps? Well, at most k to the power of n times t, because that's the number of possible operations that I can perform in t steps by choosing steps from within these k to the power of n candidates. But there are n factorial possible inputs. N factorial is 2 to the order of n log n. So if I want to sort at least or exactly n factorial different inputs, I'd better have this t factor here to be at least of the order of log n. And that's how we know that at least log n steps are needed for any proper permutation class. And there are proper permutation classes for which log n steps is the correct order. Let me show you several such classes which will play an important role in what will follow. So here's a class that I call the class of plus merges. What's a plus merge? That's an operation where you partition your input into, say, a prefix, which I colored in red, and the rest, which I colored in blue, and then you merge this red part with the blue part arbitrarily, while preserving the relative order of all the red entries and also the relative order of all the blue entries. And if you are familiar with shuffling card decks, then what I call plus merge here is what people doing shuffling of card decks will call the riffle shuffle. That's like an operation where you take a deck of cards, you split it into two parts, and then if you are skillful enough, you will merge them. So that's the plus merge. Closely related is the minus plus merge, which is essentially the same, except before merging the red and blue part, I reverse the order of the red elements. And likewise, there will be the plus minus merge, where I reverse the the blue elements and keep the red elements in the same order, and the minus minus merge, where I reverse the order of the red and also reverse the order of the blue, and then merge them arbitrarily. So these are four classes, and again, it's not too hard to convince yourself that with any of these four classes, I can perform merging in order of log n steps. Indeed, the classical sorting algorithm merge sort is basically sorting with plus plus merges in log n steps. And for each of these four merge classes, I have a corresponding unmerge class, which is the inverse operation to a merge. In terms of these pictures that I'm drawing here, the unmerge looks like a merge, except it's turned upside down and the order and the arrows are reversed. So likewise, I have four different unmerge classes. And for all these 8 merge and unmerge classes, the worst case sorting time is logarithmic. And then there are 4 classes which I will call troublemakers here, because I don't know what their asymptotic worst case sorting time is. The first troublemaker is the class of parallel block reversals that I have already mentioned. So that's the class where you are allowed to split the input into consecutive blocks and then in parallel reverse the order of all the blocks. And then there is the class reverse parallel block reversals, which does the same thing as the parallel block reversals do, except after reversing the blocks, you also reverse the entire sequence. Or in a direct fashion, what the reverse parallel block reversals would do is take some prefix, move it to the end, then take the prefix of the rest, move it after that, and so on, and so on, and so on. Again, for people who like to reason in terms of shuffling cards, this reverse parallel block reversal operations correspond to what is known as the overhand shuffle, which is what people who are not skilled enough to do riffle shuffle will typically be doing when you ask them to shuffle a deck of cards. And 2 similar-ish classes, the class of parallel block transpositions. I again partition the input into consecutive blocks. Now I can imagine that I also allow blocks of size 0, and then I take each, say, odd-numbered block and transpose it with the subsequent even-numbered blocks. And since I allow blocks of size 0, I can imagine that this fixed point here is really obtained by transposing a block of size 1 with a block of size 0. So this fits into my definition as well. So that's parallel block transpositions, and reverse parallel block transpositions are the same, except I again reverse the whole sequence afterwards. And well, all these classes are classes for which I do not know their worst case sorting time, and as far as I know, nobody else knows either. And for all these classes, the bounds that we have are the generic log n lower bound, valid for any proper permutation class, and a not terribly difficult sorting strategy which achieves sorting in log square or order of log square n steps. So hence an open problem is to improve these gaps. If you can think of some clever way to use any of these operations to sort any input in asymptotically fewer than log squared n steps, or if you can see any reason why these operations or any one of these operations couldn't sort some sequence in asymptotically log n steps, I certainly would be interested in hearing about that. Now, why am I giving you this catalog of 12 permutation classes with polylog worst case sorting time? Because it turns out that these 12 polylog classes are actually the only and exactly the 12 minimal permutation classes with polylog behavior.
Can I ask a question?
Yes.
So you didn't show that any function between log and log square could be achieved.
Yes.
Log to...
I do not know. So it is perfectly possible that anything that satisfies these lower and upper bound happens as a worst case sorting time of basically any of these four classes. I do not have any argument that would show that the worst case sorting time is either matching the upper bound or matching the lower bound, or indeed matching any like reasonable function.
But have you mentioned before that your conjecture is that everything sits on the left, that it's actually log? Or I understood wrong?
No, that's not. I wouldn't call it a
Okay.
conjecture. I really am not. Don't have any strong opinion on what would be the correct behavior
Okay. Thanks.
here.
Okay, thank you.
Yes. So anyway, these 12 classes with polylog behavior, like the 4 merges, the 4 unmerges, and the 4 block type troublemaker operations are the minimal polylog classes in the following sense. In the sense that I can show, or we can show, that if you have a permutation class, say S, which does not contain any class from this catalog of 12 classes as a subset, then we can show that such a permutation class will have a worst case sorting time that jumps all the way to at least square root of n. And here I have mentioned a conjecture which says that actually maybe instead of square root of n, the correct bound here would be linear. So here I'm confident enough to conjecture. And yes, I repeat the problem that I have already mentioned before. Can this square root of n be improved? Maybe it can, maybe all the way to linear. And the rest of my talk will be spent in explaining how this lower bound is proven, or rather explaining some of the ideas that appear in the proof. I will not get anywhere close to showing the full proof. So let me move to that, and let me move to that by giving some more terminology. So for 2 elements or 2 numbers I and j, an inversion in a permutation is, well, 2 numbers are an inversion if the permutation exchanges their relative position, and if otherwise the 2 numbers are a non-inversion. And for some constant k, I will say that a permutation is k almost monotone if it has at most kn inversions or at most kn non-inversions. Imagine here to be some fixed constant and n growing to infinity. So, well, a random permutation will have quadratically many inversions and quadratically many non-inversions almost surely. So if the number of inversions say, is linear, this means that the permutation is somehow close to being increasing. And likewise, if there are only linearly many non-inversions, then I'm somehow close to being decreasing. And well, two more bits of terminology. An integer interval is just a set of consecutive integers. And the intervalicity of a set of integers is the smallest number q such that the set can be written as a union of q integer intervals. And with all this terminology, the first ingredient in my attempt to prove a lower bound for sorting time of permutation classes is this structure theorem. So let's say I have a permutation class S, which does not contain any class from this polylog catalog as a subset. And I claim that for any such class, there is a constant k with the following properties. And let me scroll down for the picture. The inputs of the permutation, of any permutation in such a class, can be partitioned into k consecutive blocks, say x1 up to xk, and also the outputs can be partitioned into k consecutive blocks, y1 up to yk, with the following property. If you pick any of the input blocks and look where your permutation maps the elements from this block, well, it cannot scatter them completely arbitrarily. It has to map them to a set of intervalicity at most k. So any input block is well mapped to a sequence of up at most k consecutive blocks in the output. And symmetrically, if you look at any of the output blocks yj and you ask where did all these elements come from, well, they could have come from at most some k consecutive intervals of the input.
Excuse me, we have lost a part of the formulation. So could you, there exists such a partition? Okay, now I see.
Yes.
Thank you, because it was not clear where this can be was lost.
Okay.
Thank you.
Okay, so these are the properties of the partition. Every input is mapped to some k or at most k consecutive blocks in the output. Every output has a pre-image of at most k consecutive blocks in the input. And moreover, if you pick any input block xi and any output block yj, and you look at all the elements that are mapped from xi into yj, these will form a k almost monotone subpermutation. Yeah, okay, so a structure theorem. And it's an if and only if characterization, in the sense that if you look at the 12 classes in this list L, you will see they do not satisfy this structural property. Now, how can this help me in proving a sorting time a lower bound? Well, this is how I will now translate everything into graph theory, because graph theory has some great tools such as tree widths, which I want to use here. So instead of this picture of a permutation that I have been using so far, I will be using what I call the adjacency graph of the permutation, which is here on the right. And so for a permutation of size n, this is a graph with 2n vertices, n vertices on top corresponding to the n inputs, n vertices at the bottom corresponding to the n outputs. The top vertices are connected by a monotone left-to-right path, and so are the bottom vertices. And in between, there is a matching which corresponds naturally to these arrows that you see here. So this is an adjacency graph of a permutation. And what you need to know about adjacency graphs and what has been known before is that they might have, for some permutations, they might have large tree widths, as large as linear. For sure, they cannot have tree widths larger than linear since they have two n vertices, but linear can be achieved. And just like I can use a graph to represent a single permutation, I can also use a graph to represent a sequence of permutations, which I imagine as a sequence of steps in some sorting procedure. So suppose I'm doing sorting and I have applied steps sigma 1, sigma 2, sigma t, all of which are, well, some permutations. Then the sorting graph of this sequence is what you see here on this picture. So for each individual permutation in that sorting sequence, I have the corresponding sorting graph over here, and the sorting graphs of the individual steps are stacked on top of each other, and they are interconnected by n vertical edges to make all this into a single graph. So nothing terribly sophisticated. And what you have to notice is that if I have a permutation pi, which is sorted by an sequence of sorting steps sigma 1 up to sigma t, then the adjacency graph of this input permutation pi appears inside this sorting graph as a minor. Not hard to argue. Basically, to find this adjacency graph GP inside this sorting graph, what you do is you ignore all these horizontal edges except for those that are completely on top and completely at the bottom, and then this whole graph will turn into a subdivision of the adjacency graph of the permutation that is being sorted. So that's not a very sophisticated claim either. But the consequence of this is, since we know that tree width is a minor monotone, that if your sequence of permutations sigma 1 up to sigma t attempts to sort an input permutation pi, then the tree width of this sorting graph has to be at least as large as the tree width of the adjacency graph of pi. And in particular, since there are permutations pi that have tree widths which is linear, if you try to sort everything by at most t steps taken from some class, you have to make sure that the sorting graphs that you construct in this way also have tree widths at least n. So this is the core of the argument. You can probably now see where all this is going. Now I will say, okay, imagine that these permutations sigma 1 up to sigma t come from some class which has a very restrictive structure, such as the structure that I have described on the previous slide with this structure theorem. Then you may argue that this restrictive structure means that the tree width cannot be too large, unless you have lots of steps repeating on one after another. So that's a very vague outline of the argument that I'm planning to make. And let me make it slightly less vague by at least giving you a hint of how I plan to argue that some sorting graph does not have very large tree widths. So recall again, or don't, this structure theorem that I have shown you before. Now, what do we do with it? The thing is this. If you know that your permutation class satisfies these structural properties, then you can show that a sorting graph of a t-tuple of permutations from such a class can be drawn on a surface of not too large genus with not too many edge crossings. Really, if you try to do the drawing and play with paper and pencil for a while, you will figure out that this is what somehow follows from this structure. But I will not be drawing you a picture because it's not quite so straightforward. All right, so you have a graph which can be drawn on a surface of a not too great genus with not too many edge crossings. And from this, it follows that it does not have too large a tree width. And now this little word hence here is hiding several decades of research by graph theorists who studied, of course, this question of what structure in your graph gives you a guarantee of not too great tree widths, and of all these of all this line of research, I will mention the most immediate result that we depend on here, which is due to Dujmovic, Epstein, and Wood, which exactly says what I need to use here, namely that if you have a graph drawn on a surface of a bounded genus with a bounded number of crossings, then there is a formula or an upper bound on tree widths, which looks like this. And that's exactly what I need for my purposes, because remember what I told you a while ago. If you want to sort every permutation, specifically if you want to sort a permutation whose adjacency graph has tree widths which is linear, then also the tree widths of the sorting graph has to be linear. So this term t times square root of n has to be at least linear. T is the number of steps, n is the size of input, so the number of steps need to be at least square root of n. Yeah, that's the reason why permutation classes that follow this structure theorem must have sorting time at least of order square root of n, and like I said, this is not known to be tight, and I frankly doubt this is tight. Okay, so that's what I have prepared for you here. Here is a link to the actual full paper with all the details that I have swept under the rug in my talk. There's also a conference version in the proceedings of SODA 2024. And that's all that I prepared for you. Thank you for your attention.